My name is Alicia Collins. I'm your host. I am the creativity catalyst at the Brilliant Labs. And today we are very excited to have Saurabh Mhatre, who wears many hats. He is an architect, designer, researcher, and he currently is based in Cambridge, Massachusetts, in the United States, and works with the Harvard School of Design. And today he will be sharing with us about transdisciplinary design and feature his amazing projects and share the significance of collaborations. So welcome, Saurabh. We are very excited to have you here.
Great to be here too.
Right.
Okay, I'll start. Hi, I'm Saurabh Mhatre, as Alicia mentioned. Thank you for Alicia. Thank you for having me here. I'm a senior research associate at the Material Processes and Systems Group at the Harvard Graduate School of Design and at the Harvard Center for Green Buildings and Cities. I'm trained as an architect, but currently place myself in between the fields of design, engineering, science, and art. I'm going to start with sharing some important moments in my journey with you to give you a context of where I come from and what has led me to do what I do. All throughout high school, I was studying to be a computer engineer, but at the end, I decided to make a switch to architecture. Wanting to go into a creative field was something I have been leaning towards, and I definitely had a bit of influence from my dad, who is also an architect. Doing my bachelor's in architecture in Mumbai, I was exposed to both analog and digital methods of designing and making, but was still constrained at the integration of these techniques because they were not yet established in Mumbai. I became very interested in parametric design and design computation and hence decided to come to the US for my master's. I did my master's in design technology, a design research based program at the Harvard School of Design. That program exposed me to emerging technologies, robotics, material science, design thinking, and taught me about designing at various scales ranging from nano, micro to macro. One of the most important things that I learned being in the ecosystem of the university was the importance of collaboration and transdisciplinary design. That there is novelty in the solutions and opportunities that arise when architects, designers, engineers, material scientists, and people from different fields collaborate with each other towards a common goal. The societal challenges of our time demand rigorous and robust knowledge of different fields. Research cannot be done by just one person. We build on the work done by others before us, and we collaborate with people around us. Before I dive in, I would like to highlight that I've been very fortunate to get a chance to work with an amazing group of people with diverse backgrounds, not just from the Graduate School of Design, but also the Bertoldi Group and the Harvard Microrobotics Group at Harvard School of Engineering and the Wyss Institute, and many others, during my 8 years in this university ecosystem. The work I'm going to show is collaborative work between me and all of these amazing people. Throughout my presentation, you're going to see this symbol a lot, the symbol in red. In chemistry, it denotes a system or a process which is in dynamic equilibrium. There's a constant back and forth exchange of information among both the entities on the two sides. This will be manifested in all the project examples I'm going to share with you. You'll also see an interesting dialogue and dynamic shift between curiosity-based research and applied research, where we give ourselves the freedom to explore as well as at some point focus on solutions to a very well-defined problem. I'm going to give you 3 examples of projects which fall within the blurred domains of design, science, technology, materiality, and in some way contribute to the larger agenda of sustainability. First, I'm going to talk about our work on 3D printing of ceramic, a sustainable and opportunity-driven way of scaling up 3D printing in context to architecture. And then I'm going to show you 2 projects, one which starts off as a pure curiosity-based research, a project which is a solution trying to find an application, and another one under applied research, which is a solution for a well-defined problem. Due to time constraints, I won't go too much in depth in these projects, but I'm open for questions after the presentation. So, why ceramic 3D printing? 3D printing, also known as additive manufacturing, is a manufacturing process where the 3D printer creates three-dimensional objects by depositing material layer by layer in accordance to an object's model. Using these 3D printers, we can make very efficient, precise, dynamic, and beautiful creations with a variety of materials. Majority of the 3D printers available in the market cater to the desktop scale, something that you can easily keep on your table, and use commonly available plastics as the printing material. But when we think about 3D printing of larger objects like buildings, we can't imagine printing tons and tons of plastic. It's just not sustainable. And hence, materials like ceramic and concrete come to mind. Majority of the large architecture scale 3D printers are 3D printing concrete. But we believe that ceramic holds a lot of promise as a sustainable option, and when paired with robotic workflows, can drastically reduce the carbon footprint imposed by the construction industry. I would categorize this into an opportunity based research. For the last few years, we, the MAPS group, have focused on studying conventional ceramic manufacturing and forming processes and researching on how integration of emerging technologies can add novelty to not just the industry, but also help achieve larger goals like customization and sustainability. I'm going to focus on two projects, one which looks at the 3D printing of a single body of clay, and another where we are co-extruding two different bodies of clay together. The project Ceramic Morphologies utilizes a clay extrusion system and a three-axis armature to produce 552 unique ceramic elements for the pavilion to be exhibited in Spain. Each element is sized according to its position within the structure, the dimensional constraints of the printing bed, and a maximum allowable toolpath length. We developed a novel computational approach to generate a surface geometry of the pavilion, discretize the form into individual bricks, and accommodate for the frame. Toolpath geometry and machine code is also generated directly within this parametric model. The digital workflow enabled us to account for shrinkage of the clay during drying and firing process, reduce overall printing time and material consumption, and tune the stability of individual bricks. Here are some shots of the pavilion. The outside surface was smooth and the inside surface was bumpy, which was based on research on thermodynamic heat transfers of different surface geometries. This project shows that using CNC or robotic technologies with ceramic enables the vision of mass customization rather than mass production. In this project, all the material testing, workflow development, and prototyping was done in-house at the university in collaboration with the Harvard Ceramic Lab, and the knowledge was shared with the Institute of Ceramic Technology, Spain, who did the final production. After having developed a workflow for the efficient printing of one single clay body, we wanted to see what opportunities arise when we are able to print multiple bodies in one single print. Is it possible to print two different clay bodies with different mechanical performative properties in a single module? Can we imagine our walls having a single material, ceramic, but performing differently across the section? Some areas taking the load, some areas offering thermal insulation, some areas being super porous and lightweight, all within one single homogeneous form. That's what we explored in Project Janus. Janus is the god of transition and duality in ancient Rome and hence seemed like an apt name for the project. Throughout a process, we always look at examples from different fields as a start point. In this case, you can see that the method of extrusion has been very well studied and mastered in the food industry for the manufacture of a lot of commonly known food items, ranging from sweets and different ways of making different shapes of pasta, all the nozzle designs and research. The same is also well developed on the in the polymer extrusion industry and academia, especially in the design of hierarchical coaxial nozzles. In simple terms, basically how you can have multiple nozzles once inside the other, extruding different kinds of materials. We thought, wouldn't it be cool to do the same with ceramic? What design and application opportunities would it open up if we are able to achieve a multi-material 3D printed ceramic workflow? So building on a previous work, our setup consisted of two tubes of different bodies of clay ceramic, red and white, with similar shrinkage and water absorption properties filled in a tube of a screw extruder, which basically in simple terms is a big syringe, which is mounted on a 6-axis ABB robotic arm, which is conventionally used in complex fabrication processes like assembling cars, etc. The two material tubes were aligned at an angle of 45 degrees, as it reduced the length of the travel from individual clay cylinders to the final nozzle, as well as increased the travel length after the point of intersection to counter the material stress. So basically, the 45 degrees had a huge impact on making it easier for us to extrude both the materials together. Ceramic as a material goes through shrinkage in multiple phases from its first stage of printing to its final stage of firing. That's why it was very important for us to select two bodies with similar shrinkage rate and water absorption, so as to eventually, when after co-extrusion, we can prevent a lot of cracking because of or similar properties. The design of the nozzle played a very vital role in the process. After a few iterations, we narrowed down to two designs. The Janus nozzle on the left, in which we could print two materials side by side, and the center core nozzle, which would allow us to print one material inside the other. Both had a lot of potential in the design affordances that they could offer. But for this project, we decided to focus on the Janus nozzle because there was more design space to be explored with it, given the degrees of freedom of the robot that it would be mounted on. In simpler terms, when you look at the red axis on the nozzle, which is here, uh, if you rotate the nozzle around that axis, it gives you more unique possibilities in the Janus nozzle as compared to how it would have come in the center core nozzle. This is how the extrudate, the material that comes out of the nozzle, would look like for both cases of this nozzle. So using the Janus nozzle, multiple tests were performed to explore the design space and establish a relationship between the various parameters of extrusion, like robot speed, the height at which each layer is printed, the bead width, which basically shows the width of your printed ceramic co-layer, the extrusion rate, etc. We tested different dimensions from lines to surfaces to solids. Once we got a hang of these parameters, we started testing them out on flat toolpath objects. A toolpath is a line that the extruder tip will follow. Using these objects, we also started testing the different relationships between the parameters. For example, keeping all other parameters constant, increase in the robot speed reduced the width of the printed bead, and a decrease in the robot speed increases the width of the bead. So in the right image, as you can see, by adding a slight increment to the robot speed, as we go from like the bottom right to the top left, we got a decrease in the bead size. And hence, because of the geometry, that decrease resulted in the changing levels of porosity throughout the tile. We also experimented with three-dimensional objects where the toolpath was static and the nozzle orientation was dynamic, as well as some forms in 3D. These are after the fired stage. our computational workflow from digital geometry to the robot code, which is basically instructions you send to a robot via a plugin called Machina, which was developed by one of our team member, to the printed geometry worked quite efficiently. Based on the rotation of the fourth axis, we were able to accurately determine the deposition of a particular material where we wanted it. This helped us to know exactly the effect the angle of the extruder, which is the fourth axis of the robot, would have on the printed path, as well as how the path would be seen from the top view as well as the side view. As you can see here, where each and every path which corresponds to a particular rotation, you can see how it was going to be visualized from the top as well as the side, which would be seen from the right side of the bead. Knowing this, we decided to create a proof of concept of our research to be able to take as input a black and white image, and our script would divide the image into horizontal toolpaths and rotate the nozzle of the extruder 180 degrees at the fringe of the black and white image layer. So for example, at a point where we see layer number 45, we have the extruder going through the toolpath in a particular direction, but as soon as it detects a change from the white side of the image to the black side of the image, the extruder, the fourth axis, is going to perform a 180-degree turn, which you can also see here. And hence, we can very accurately make it show print one particular material in certain areas of the image as compared to the other. Here is a video of the process. I'm going to just skim a little bit through it. So. And here are the fired versions of the printed tiles. For us, the two different colored bodies of ceramic were just placeholders to develop a workflow to print two materials together. In some of our current work, we have one body of clay with high mechanical strength in order to take loads, and another body, which is a very porous and lightweight ceramic foam, to act as insulation, all printed within one single brick. Hence, instead of using a lot of different kind of materials, the same that we find in a typical wall section of a house where you have different materials performing different functions, can we envision that the same performance can be done by the single material of ceramic, but having different properties embedded within it? The next project I'm going to talk about is Kiriform. This project falls in the curiosity-based, opportunity-based research domain and is a solution looking for an application. I'm going to start off by highlighting the differences between rigid and compliant mechanisms. Rigid mechanisms require a lot of parts, are complex to assemble, and prone to wear and failure. Compliant mechanisms, on the other hand, are lightweight, low cost, easy to assemble, and require minimal actuation. Kiriform is a patented system that uses material elasticity and geometry to go from flat to 3D with minimal actuation. This mechanism leverages buckling, which is conventionally something that you always try to avoid in structures and construction, and it uses it for its deployment. This is different from bending this is different from bending based on the direction of force that is applied. So if you look at my video here, if you look at bending, the direction of the force would always go up or down, but for buckling, your force is always going to go perpendicular to the cross section, and this is what happens when sheets buckle as compared to bending. Kiriform is manufactured out of flat sheets of elastic material with simple fabrication techniques. It is fast to assemble and requires minimal hardware, making it cheap to manufacture. It can be divided into two types based on It can be divided into two types based on the method of actuation. Right now, one of my video is not playing, but I'm going to continue. From the perimeter as compared to the outside. With the help of our parametric model, we have control to change all the essential parameters of the geometry, from the diameter of the mechanism to the number of fins and widths of fins, etc. Our developed parametric model makes the system applicable to a wide range of scales, from small medical devices to larger furniture and structures. The system is suitable anywhere fast and compact deployment is needed, as in the following examples. We have successfully developed Kiriform at the millimeter scale in collaboration with the Harvard Microrobotics Lab. Kiriform can be integrated in optical devices with moving parts such as lenses and diaphragms. Its aesthetic qualities are also suitable for the design of household products such as lampshades and lighting fixtures, where the intricacy of the geometry creates interesting patterns both as a static object or even better as a dynamic one. The compliant transformation of the system can be used to modulate the intensity of light, creating an analog dimmer. Kiriform is suitable for furniture designs that can be shipped flat and deployed very fast by anyone with little effort and no tools. The method of fabrication is dependent on the scale, which in turn determines the thickness of the materials used. It is compact to store and transport and easy to deploy. Its geometry facilitates the creation of functional and affordable products while at the same time providing minimal and elegant design aesthetics. As you can see from the above examples, different scales of this mechanism can be manufactured from different materials and different processes. Some fabrication processes make sense at certain scales. As a side note, we also have a very good agreement between our experiments and simulation, which I decided to keep on the backstage of this presentation. Those interested can check out the paper we have published on the same in the Advanced Functional Materials Journal. In conclusion, Kiriform is a technology with high parametric flexibility to cater to applications at various scales where rapid deployment is essential. And again, to reiterate, this work would not have been possible if it wasn't for uh, various people at Harvard from different labs who I collaborated with at different scales, from micro robotics to all the fabrication lab who were able to help me create large scale prototypes. Okay, so onwards to the next project. The pandemic has been the most dramatic disruption to human activity in a generation. For many designers, it has been a time to refocus and rethink and reflect how we design products and how, as designers, we can use our skills for the greater good. For our project, the Apollo Isolation Hood, our problem was very well defined, creating a barrier to separate the doctor and the suspected COVID positive patient, and hence reduce the aerosol spread of COVID. The Apollo Patient Isolation Hood is a localized negative pressure ventilation system for hospital beds to help contain the droplet spread of COVID, including during aerosol generating medical procedures such as intubation and extubation. The hood encloses a patient's upper torso and head in a negative pressure environment. It provides barrier protection between the doctor and patient, aerosol control via the negative pressure environment. And this project is a collaboration between the Harvard School of Design, the Mass General COVID Innovation Center, along with Boston Children's Hospital and other industrial partners. In our meetings, the doctors from Mass General Hospital and Boston Children's Hospital provided us with 36 guidelines to design a hood and their weighing of different aspects of the hood as per priority. Some of the important to summarize aspects of the hood that they wanted were transparent, easy to manufacture, is able to adapt to different sizes of people on different beds, lightweight, impermeable, as well as optically clear. As a group, we looked into multiple options of enclosures which would be deployable and easy to make. Because of the severity of the pandemic, we were on a very strict timeline and wanted to look at forms which were easy to fabricate and very easy to assemble with minimum effort. That's why we started to look at techniques of origami, kirigami, and bending, a technique of some techniques of creating volumes from flat sheets. As we were in lockdown and we had lost access to the fabrication lab, we started simple by using paper and simple knife cutting tools to make small prototypes of a design, while also speculating the material and process needed when we needed to scale up to a larger version. Simple origami techniques were a good start and could easily be scaled up using thin sheets of PETG plastic. One drawback with origami was it was always accompanied by edges and creases. Hence, to omit the edges and get optical clarity, we started bending instead of folding. So everywhere where there was a well-defined edge became a smooth bent surface. The plastic needed to be thin enough to fold and bend, but stiff enough to keep shape and not wobble. The bending and locking also added a lot of structural stability to the forms. Here is one version of the hood where we designed. I'll use this to explain how it would fold. So as you can see, the overlapping blue ports are the ports where the doctors would be actually inserting his hands to operate on the patient. And the way it folds is that, as you can see the small paper model on the left, how you have one small conical point or a pivot. So these two conical pivots are going to be the guiding circles for side A1 to match again on the side A1. And there's a it will be better shown on a video. So as you can see here, assembly of a miniature scaled version of the hood. Hence, seeing potential in this design, we decided to make a full-scale version of the same with PETG plastic of thickness 1.5 millimeter using the Zan cutter. The best aspect of these forms was that they could be manufactured from a single flat sheet and needed minimal joinery. The doctors from MGH tested this in a lab as well as at the hospital. Over the next few days, we prototyped through a lot of different iterations, taking into account the guidelines, stabilities, tests, doctors' feedback, etc. Some of these stood out as viable options, which satisfied most of the critical guidelines highlighted in the start. They did have some demerits though. Looking at the pros of all the most promising options, we designed the final hood which had the best parts of the above options and none of the demerits. So this was the final option, which we called the Apollo 3. And as you can see, it has the two arm ports for the doctors. It has these side films, which would go and fold here. It has a base plate, which attaches the hood to the base of the operating bed. And it also has an extra arm port here for emergency procedures. So we can see in this video the way it's fabricated. It can be cut in less than 20 minutes and it can be assembled under 1 minute with minimal joinery. And because it's compliant, it can also adapt to different sizes of people as well as beds. We were able to use a thinner material in the Apollo 3 and by some smart overlapping of geometry, give a double thickness layered wall where the most strength was needed, which was at the back here, which you can see on this side. Here are some detailed shots of the hood. The Apollo 3 was made up of a flat sheet, was easy to manufacture, had minimal joinery, and assembly was lightweight, was compliant to cater to various body types, optically clear, and stackable. We made 3 final prototypes in-house for a start and 20 more later after approval and sent them to Mass General Hospital, and 50 more later after which was manufactured by a company which my friend started. Design is an iterative process. There's a lot of back and forth. Here we see that what I call like the process prototype feedback loop. Prototyping at different scales informed each other, and they were constantly informed from the feedback given to us by our colleagues in the medical fields. Communication and teamwork were very important part of the process. Due to material scarcity and supply chain issues.
There's audio.
Hello? Can you hear me?
Yep. Now.
Communication and teamwork is very important part of the process. Due to material scarcity, the supply chain issues, we had to be very mindful of the plastic we used. PETG was in short supply, and most of it was being used to make face shields. Any minor changes that we made were directly on the full-scale models, and major changes were first tested on the small scale before translation into full scale. This project was a collaborative, non-hierarchical effort of more than 200 people, possible using online communication via Slack and Zoom between designers, engineers, doctors, and industry partners. All files of the project have been made open source via GitHub to help disseminate this knowledge to anyone who wants to make a hood. It started under strict fabrication constraints under the COVID lockdown, was translated into full-scale prototypes with the constant feedback from doctors and other designers, was tested in the Mass General Hospital, and now is currently on display at the Cooper Hewitt Smithsonian Design Museum in New York as a part of the Design and Healing Creative Responses to Epidemics exhibit, which is going to be on for another year. So if you get a chance, you can visit. And that is it. I am open for any questions and comments. Thank you.
Thank you so much, Saurabh. That was incredible. Super amazed to see just the sheer diversity of projects and like how many skills and fields it kind of blends together. Um, we are open for questions now. I have a lot of questions, but I want to give others a chance. Feel free to use the chat, or this is also the time you can unmute yourself or turn on your webcam and just ask Saurabh directly. While we are waiting, I want to ask that you talk in your presentation, you mentioned about the compliant mechanisms. And Kiriform is, I think, a very, very brilliant representation product of that, utilizing that technique. But I know that for somebody unfamiliar, it's also not as easy to begin with. So what's your suggestion for people to explore different prototypes or get experimental with that? What would you advise them?
I think for me, like personally, like Kiriform has always been my sort of pet project. And like for me, it's always about like, so if you see my office around, like I just like have a lot of these sort of interesting material behaviors or inspirations all around me. And always starting with very simple materials. Like for us, a lot of times when we do processes like laser cutting, right? We always have some offshoots of some plastic strips or something. And I always felt like, oh, maybe how can we use these for making art, or how can we give this like a second life? And when you're playing with a sort of like these mechanisms, at some point you realize like, oh, this could be an interesting behavior. How can we start aggregating these parts, and can this become something meaningful? Or maybe yes, maybe not. Maybe it just becomes art, maybe it doesn't have any function, or maybe it could come to a point where it develops into a mechanism like Kiriform, which suddenly almost like has its own platform technology, which can be catered to a lot of different applications.
Thank you for sharing that. How long did it take for you, like right from the conception of the project till its like
So,
actual implementation?
so for me, like especially like Kiriform, it almost started it's a very funny story of how it sort of came about because I was actually working on a different project at that point where I was trying to work with these like elastic auxetic structures, which when you press from one end, it also gets contracted from the other end. And I was trying to find a method to push this weird model from all different sides. Okay, and at that point I was like, oh, maybe I can use some sort of a camera iris or some sort of a buckling mechanism like Kiriform to be able to just do a simple rotation, but that would lead to pushing of this model from all sides. While I was exploring these options, at some point I made the fins of it super thin, and instead of pushing the fins in the direction of the model, it started buckling, which for me at that point was not what I wanted. But I just saw it, but I found like, oh, but this behavior is interesting. So let me like keep it on the side and start exploring this on the side. So even though it was not useful for the project I was working on at that time, I did see that it has potential. And this work, I started doing it on my side. And at some point, I took it to the director of a lab who eventually saw potential in it too. And then I decided to like take it as a part of my actual formal work in the lab. And it's been almost like 5 years that like from the moment I started to where it's come till now.
That's amazing, especially like the ways like all your projects have various applications. And that brings me to my next question. I mean, I know that you are, I mean, what would you consider? You're trained as an architect, as a designer, but even within those streams, when I look at your projects, I mean, it's for every field. You talk about healthcare, you talk about product design. I mean, you talk about like textile design or their housing, their furniture and stuff. It's kind of there. So, I mean, what would you suggest for people who are aspiring to pursue these fields?
It's like personally, as I mentioned in my journey, like definitely getting trained as an architect made a huge difference for me because it sort of, and also the context of Mumbai, right? Like, so getting trained as an architect in Mumbai, I got exposure to like a lot of different ways of designing and making things. When I came to the US, there was a huge change in mentality also, where in the US, if you're trained as an architect, I realized that you don't have to stick to designing buildings, but you have the kind of knowledge and background to be able to design at different scales. Conventionally, architects always limit themselves to a certain kind of scale of the building, but because I was in this sort of research ecosystem, which I love mentioning, where I got exposed to like the different labs at Harvard working on small robotic bees and in one level, or even a lot of work which is going on in the media lab where they're using like bio-inspired design. So just being in this environment exposed me to a lot of these different techniques, which at that point I did not know if how they can be directly translated. But for me, just having an open mind, attending as many events or trying to listen to a lot of like people in this ecosystem who are doing cool work, like sort of I started realizing that when I'm working on projects, I was remembering, oh, this person is doing really amazing work here in this field or that field. And that's where also like the whole idea of collaboration came, where I know as an architect I have only a few set skills. I don't have mastery over everything and I don't need to. And that's the best part about these collaborative environments, where you with a particular field can work with other people from different fields, and in a very sort of like in a non-hierarchical way, and it's going to do good to both your fields in the end, you know.
Thank you for sharing that. I'm curious to hear what our audience have to say. Any comments, questions from you guys? I see somebody's typing. Again, feel free to unmute yourself. Again, I'm just super amazed when I see all these projects, and I'm curious about like what's your favorite part of your design process? Like which stage do you like the most and what you find the most challenging?
Well, I definitely am a fan of like the exploration part, right? Like what I mentioned, like I touched upon in the start during like the sort of typologies of research, right? Like where you give yourself a certain amount of time to explore different sort of um, ways to go about things, like giving yourself a flexibility, like nothing is wrong, right? Like you're just like trying to play with the material. It's very hands-on. You're sitting with a group of bunch of people ideating, oh, what if it could be this or it could be that. And again, which brings it down to like, as a designer, when I'm sitting down with like people from material science or engineers and doctors, and then we are like, we all bring a certain kind of baggage of our field to the table. And we always like are like we always have our opinions which are biased based on our field training. And when you sit down with people of different fields, you realize like, oh, even this could be done that way. I would never have thought of this, and that for me is the best part about my sort of like experience with this project, is like the sort of interaction I have with people from different fields, trying to see how can I learn different methods that they use in their fields. Like I'm a I'm a very tech savvy person. That's why even as an architect, like I love getting trained on a lot of these sort of machines and instruments that they use in the material science field to quantify a lot of behaviors which we as architects do not exactly go too much in depth with.
That's great. Susan Kelly has a question. How do you deal with disappointment and frustration when your projects don't work out of the way you wanted?
That is a really great question. I guess for a lot of projects, whatever I showed you definitely is like the sort of like taking all the best parts about this project, which I am showing it to you. There's been a lot of like aspects within these projects which there were points where things are not working, and it's like at some point you feel like, oh, you don't know where this thing is going. But for me, I was fortunate enough to be working on a lot of different projects at the same time. So for me, it was great to, sometimes you get so engrossed in one project, it's not working. It was good to just like keep it on the side, keep it on hold, work on something else, and at some point eventually just have, oh, an idea of like, oh, maybe I could have tried it some different way. So just giving yourself a certain sort of like detachment from it and then coming back to it has helped me.
That's really cool. I guess we all, no matter what field we are in, kind of deal with this kind of situation. What would you suggest for people to like foster more collaboration opportunities or network? What would be your advice?
For me, I think for me, it's always been funny because especially like coming from Mumbai, it was a it was a big change in terms of the whole idea of networking because uh, in at least throughout my bachelor's education and stuff, like there was nothing formally called networking, right? Like that's just something which is like there, but I got to realize it more when I came to the US, which was a very sort of formal setting for me. And for me, the whole idea of networking is just about like, I never do it in a very conscious way, but I just like try and like I'm super curious. Like I really love to know things, and when I see someone present something really interesting and I have a lot of questions, I always like keep in touch with that person and start like like having these like in-depth conversations about certain aspects which interest me. And when sometimes in my work I find out that, oh, maybe there's certain aspects of my work that fall in this domain of this person who gave a talk, let me just have a chat with him and talk to him about it and let me see what he feels. And because he's an expert in that field, instead of trying to know what direction I need to take, I always prefer talking to people first, seeing what they know about that field, if there's anything novel about what I'm doing or it's already been done yet. So it saves me a lot of time to, in the initial stages of the design, to have these conversations. So keep an open mind, like talk to people from different fields, like try and attend as many things especially which might even not fall in your like domain or like comfort zone. Like there's always something that you learn from these things.
Sadly, we have only time for one last question from Sanjay Mhatre. Are you tinkering with marrying these ideas into the metaverse? What are your directions, suggestions?
Well, even though, as I mentioned, like I am a super tech savvy, like pro tech person, like I do feel a bit sort of uncomfortable looking at ideas of metaverse, and especially like I love sort of placing myself in between the domains of the physical and the digital. And right now, most of the ideas of metaverse are sort of like completely digital, like you being, irregardless of what physical space you're in, you are engrossed with your headset in this digital um environment. And for me, what is more important is how can we start correlating physical objects, and how can we create digital twins where physical objects, the things you, the way you interact with physical objects in your physical world, how can that be translated into the metaverse and vice versa. So not completely promoting the digital aspect of the metaverse, but trying to see how can we have a good correlation between the physical and digital.
That's a great question for all of us to ponder upon. I would like to thank you again on behalf of our whole Brilliant Labs team. Thank you so much for sharing such incredible work. And Saurabh, you're a very humble and also a very approachable person. So if people have any questions, I'm sure like you can follow him on social media. He also shares his amazing art via his Instagram and Twitter. So I would highly recommend checking it out. Thank you again, everybody, for joining this session. And we look forward to seeing you next month. Thank you again.
Thank you so much, Alicia, and thank you everyone for your time and attention.